Hello and welcome to another video. So I decided I'm actually going to do maybe like one or two more of these on-sites just so we get something a little bit more challenging compared to the Uber one. Obviously variant. So this one actually has the lowest pass rate, so we'll do this one, see how it goes. Maybe we'll do a couple more if people like those or if it's fun. And then go back to system design after that. So let's do this one. So 4 questions, 2 are same thing. Alright. Transpose. Okay, matrix flipped over main diagonal. I think this one's pretty straightforward. We just want to loop through the rows and the columns up until the center, and we basically want to flip the row and the column. So this one's like should be looking easy or whatever, so you can don't need a lot of time to talk about this one. So columns are, let's go rows over 2. So let's see. If the rows is 3, we'll go to 1. Fine. Yeah, right. We'll go to 1. Yeah, it's fine. If there was 4, we'll go to 2. Fine. Yeah, that's good. And we just do a basic transpose, so we need to swap 2, so this one with this one. Alright, so let's just make sure we're not like swapping, we're not doing things multiple times. So let's say our matrix is 2 by 2. So this. So we're gonna swap these two. Yeah. Actually, will we? Yeah. But we want to make sure we don't swap twice. So in this case, this would be swapping twice actually, because like this is 1 0 and 0 1, and we're gonna get to that again and again. So we could have like a visited, that would be easy. But if we want to do in place, then what we can say is like yeah, maybe we could say like if the row is less than the column or something, do it as well. Then do the swap. Because essentially, well, we actually do need to swap these back elements as well. And so if I go back to this example, we actually do need to hit like this, which is like the later part of the matrix. So yeah, I think instead of that, we just do this. And then we just have an if statement here. So if row is less than column, we do this. I think that'll work. Let's find out. Alternatively visited set, obviously. Might be a better way, but just quickly, let's go for it. Obviously, creating a new one's going to be way easier. Oh, okay. So we do actually have to make a new one because the dimensions might be different. Yeah, we have to make a new one. So there's nothing we can do about it. Yeah. So we have to make a new one actually. I didn't think of that. So that's kind of bad. So this is 3 by 3, but it's not always going to be 3 by 3. So if it's like 2 by 4, we have to make it 4 by 2 and so on. So we have to do a new one for sure. So yeah. And we can actually, yeah, it's fine. Okay. So like 0 or something. I mean, actually, technically, I think we can just do it in here. Let's find out. Let's see if we can just do a list comprehension, just do a return. See what errors we get and stuff. That'd be interesting. Haven't done one in a while. So 4, 10, and range columns. So this is going to be matrix. Yeah, maybe I'm going to do this wrong, so we'll see. Matrix CR. Yeah, I don't know if I can do it in this format, actually. We'll see. One. Okay, so let's see what this 2, 3. Yeah, this is definitely sloppy for sure. Okay, so we got the same. So we didn't swap at all. Interesting. All right, let's just do a 0 and let's do a normal one, and then that'll work for sure. So we'll just go like 0 for now. All right. Now our dimensions are different. So our actually dimensions here is in range calls. So in range rows. Then this will be result or something. Okay, so this is the actual rows of the matrix. This is the columns of the matrix, and then matrix row column or result is the old matrix of column row. I think that's right. Let's find out. Okay. I'm not sure what was wrong with the list comprehension, but yeah, I could probably Google it or something. In an interview, I probably wouldn't try to have complicated list comprehensions, I guess. Okay, anyway, moving on. Given the availability time slots of 2 people and a meeting duration, return the nearest time slot that works with them. Okay. All right. Okay, so, okay. Given the availability time slots. Okay. 60, 68. I see. Okay. This should be pretty straightforward. We just sort both availabilities and we just compare similar ones, and then we just move whichever one is smaller, and then we just keep comparing 2 until we run out of bounds, and then we return nothing if we couldn't. Okay, so should be pretty straightforward. Hopefully I don't make 20 mistakes. All right, I equals 0, j equals 0. So while I is less than slots 1, j is less than length slots 2. All right, so essentially we just compare them and we see how much of an overlap is there. And if there is enough, we will use that. So if one is smaller than the other, like if so there's going to be like 3 possibilities essentially. Slots like this guy is before this guy is after this guy, or overlap. We'll check for before and after first and increment. So we'll go like this. All right. So if y1 is, I guess also we have to have the case of, like, if they're 10 to 50 or something, time inclusive. And the duration of the meeting can be what? 1? Okay. Yeah, so if it's like 50 and 50, that's still enough. Okay, interesting. All right. Yeah, from start to end. Okay. So if y1 is less than x2, then we will do this. Just do a continue here. If y2 is less than x1, okay. So now we have the overlap case. Now we just figure out like how much time there is. So time will be the max of or I guess like x or whatever. Okay, let's just do this. So it's gonna be the one that ends earlier. So min y2 y1 minus max x2 x1. So for example, if we have like 60 and 120, we'll get, or these two, we'll get 70 minus 60, so we'll have an interval of 10. So if time is equal or greater to duration, return max x2 x1 is the start, and then this okay, so 60 to 70, so this is saying this is 10. This is saying, interesting. So I would have thought that the duration, like I would have thought that this would actually be 9, because like 60, 61, 62, 63, 64, 65, and so on. I guess not. So then in that case, okay, I think this is fine then. Yeah. We'll see. Like, there might be some weird edge case. I think this should actually be 60 to 67, but we'll see. And then this is just the same thing plus duration, right? Alright. Else we just increment one of them. Doesn't matter which one. Alright, and then we just return this. Okay. Let's see. What's the duration? Let's see what we get here. So 1060. Okay, this will be sorted. These two will be here. 2129. So in this case, oh, it actually does matter. Interesting. Okay, so I didn't think of that. That's also bad. So if they do overlap, you actually want to increment the one that ends first. Yeah, so that was actually pretty bad. Okay, so yeah. So elif, yeah, so same thing. If this can clean it up as well, obviously. All right. Yeah. No, this is wrong. This is y2, and this is else. Okay. So basically, whichever one ends first. Yeah. Okay. All right. Let's go with that. Okay. Okay. Nice. Let's clean this up a little bit before we. Okay. I have time. We don't need an else. I think this is good. Okay. Yeah, this is fine now. I mean, obviously we can do some smaller things like, I guess, yeah, we can definitely do some smaller things. So we can call this like x3, y3. Or x shared or something. Definitely better variable names, but yeah. x3. And then this will be x3. All right. Cool. What happened? What happened? Oh, right there, the wrong way. Okay. All right. Moving on. Write a square for the sum of every pair of adjacent elements of a perfect square. Given a return number of permutations that are squareful. Two permutations are different if there's an index I. Okay. Permutations I. Okay, so I believe permutations, like, you can have the same elements in different orders, so like this is different than this. Okay. Seems like the hard one, I guess, in this, so I guess we have plenty of time. Okay. Permutations that are squareful. Okay. So, how does this work? I guess. Okay, yeah. Backtracking? Just simple backtracking? Does that work? We just try random numbers and we just keep checking if it's squareful? Right? Every time we just take a random one and we put it back in? Seems good. Yeah. Now we want to avoid having the same permutation. So we can just build permutations and add them to like a set. Is that what we want to do? And that's one way. So essentially you build. So how many permutations can you have actually before we even do this? So if there's 12 numbers, we essentially have like 12 times 11 times, right? So what's 12 factorial before we even, that's a lot. But the nice thing is I think for these backtracking, you might think you get TLE, but then like not all of these work. I mean, I guess maybe it's possible to have all numbers that always work. But yeah. Okay. Alternatively, is there a way we can like calculate it? No, I mean, let's just try backtracking first. I think that's going to be... And if I was given this in an interview and like I wasn't like, this isn't a lead code thing, I wouldn't see like, would this get a TLE? Yeah, let's just try backtracking. Let's try some optimization, some early ends, things like that. Okay. And so what do we actually need to store? And how do we, is there a way we can avoid the same, like, is there a way we can avoid the same permutations without actually building this up? Like maybe we store just the last number or something, and then we avoid multiple. Okay, let's just get something working, and then we'll make it better. I guess that's a good way. Okay, so let's go with set, and we're just gonna like build a tuple of like all these numbers or something in that way, or some weird, yeah, something like that. Okay. So let's turn these nums into counts so then we can go through them easier, because we're going to be taking out numbers and putting them back. Right? Yeah. I wonder if with permutations, the way we can avoid it is just we have counts, and then we just make sure we don't use the same number again in the same place. Because as long as that's the case, then we're good. Right? Like, as long as there's one difference. Yeah. I think, let's try that. So let's actually make this this. Now have no cur. And we're just going to pass, the last number we had. And then when we put in a new number, all we need to know is the number we had. So for example, if we had a 1, then we try some number and we just see like, is this a square? Right? And that's it. Okay. So first let's go counts, get a better format. Then we go, all right. Then, so we can include a couple things here, I guess. We can include the length maybe. Or yeah, cur or total or whatever. Let's go with length. This is just like a quick way of knowing how many numbers we have in our current thing. And then last. So if length equals length nums, then we basically have a permutation. So we'll just go that. All right. Now, yeah, and so last is actually pretty easy. In the beginning, we can just pass 0, and then that way, like, actually, wait, the two numbers have to be next to each other, right? Yeah, okay. So if the, so essentially if we're on the first index, if length is 0, then we can just try every number and we're good. If not, we're going to try to make sure that the number we're putting in plus or last is a square. And then do that. All right. So for key, so for key val in counts items. So if there's a value, right? If the value is non-zero, then we can do it. So if length is 0, then we'll just go for it because anything works. So we'll go backtrack 1 and the value. We also, the key. We need to decrement the key. That's going to be a problem. I think we want, I don't think we can decrement items and do an iteration, so we'll go like this instead. Counts key is non-zero. Okay, we'll go counts key, subtract, backtrack, and then add again. All right. Otherwise, we need to actually make sure that this is a square. So if square root, how do we quickly check if it's a square? I think you can just square root of last plus key mod 1, I want to say, is 0. Then this is a integer. Perfect square. Then we'll do the same thing, right? So bam. All right, we'll give it a go. And obviously you can do this. If you don't want a variable outside, you can do this. Return 1. And yeah, so this should also work as well. I did that. All right. So I guess we got a lot of time, so we can debug, and pretty confident this is going to be good, but we'll take a look. Because we're not building, we're building quick. Yeah, we'll see. So length 0, last is 0. Cool. All right, let's go for it. Yikes. All right, so let's read the code again. Let's just double check. Let's try to follow the logic. All right, so 1, 1, yeah, okay, good. Okay, so in the beginning, this is not true. For key counts, if counts key is non-zero, okay. If length is 0, counts key is 0, okay. So counts will be 0. Result will go backtrack. Why are we doing 1? This is not 1, right? This is length plus 1. Mistake. Let's see if we can catch anything else before we try it again. Okay. This is fine. All right, so let's say we recurse. So this is 0 now, so we can't use that. So we'll go to this key, and we'll say, okay, can we do 17? We'll go to this case. This should be false. So 17 doesn't work. Okay. Then we'll go to 8. Go to this case again. Last is 1, and key is 8, so this is true. So then 8 will be 0, then we'll backtrack again. So now length will be 2. This is the only one that, so length will be 2, the key will be 8, and this is the only one left. Then we'll try this one, and this will be fine. Then we backtrack, then we get that, and then we're good. Then we'll return. Yeah, and then we'll try, there's nothing else that can work with 1, so then we're going to pop everything. Then we're going to try 17 first. Which is fine. Then we try 17. Then we try 1. That won't work, so we skip. Then we try 8. That'll work. 2. Yeah, I think we're good. It's good to go. Okay. Nice. Okay, yeah, so these backtracking, if you just do like the brute force math of like how many permutations and stuff you have, it's usually more than you can have, but because you have all these like optimizations and like early returns and stuff, it usually ends up working. And that's probably what I go with in an interview. I'm curious if there's something else. But yeah. So pretty happy with that, honestly. 25 minutes. Yeah, 25 minutes. This one definitely could have done better. This one was fine. Oh, I did miss some tests. So yeah, so I guess the main things I'm going to focus on, I think maybe what I will do is I'll do a couple more, but instead of just running the code, we'll do like some dry runs or something. So the goal will be get it down, try to fix coding mistakes, try to find all these things that I'm taking for granted that I can just like run code so that we can focus on like actual debugging, right? So like here, like I should have caught that you can't just like increment one of them. You have to increment like the smaller one. That's pretty obvious, but I just was like, whatever. So yeah, we're going to do like some dry runs and stuff and instead of just running stuff. So I think I will do more of these onsites. I'll just do the onsites. I think the other one's a little bit too easy and might be like 5 minutes. So we'll go on the onsites and try to improve code quality and yeah, that stuff like that. Yeah, pretty happy. So yeah, hopefully you like this one. If you did, please like the video, subscribe to the channel. Let me know what I can do better, things like that. And yeah, so I'll probably do, let's see. Yeah, and then mock. Yeah, so I guess we'll do the Meta one, we'll do the Amazon one. Yeah, I guess we'll just do all of them. Be fine, right? It's like 1, 2, 3, 4, 5. And I'll just only do the onsites. Just wait. I think these are a little bit too easy, so we'll just do the onsites and yeah, focus on those things. So, because in like a lot of these companies, right, you can't run your code or anything like that. So we'll just do that. No autocomplete. Do dry runs and then make sure we try to catch everything. Yeah. Okay. So thanks for watching.